Hi everyone, my name is RVS Harshini. Welcome to my YouTube channel. Today we are going to discuss on digital signal processing. Let us see the topic. Today we are going to discuss on the Fourier transforms and its applications in signal processing. Introduction to Fourier transform. The Fourier transform is a mathematical technique used to analyze functions in terms of frequency. It decomposes signals into their constituent frequencies, allowing for better understanding and manipulation. This transformation is crucial in various fields, particularly in signal processing. Now, let us see the history of Fourier transform. The concept was developed by Jean-Baptiste Joseph Fourier in the early 19th century. Fourier proposed that any periodic function can be represented as sum of sine and cosine function. The foundational idea paved the way for modern signal analysis techniques. The mathematical definition of Fourier transform is the Fourier transform converts a time domain signal into frequency domain representation. Mathematically, it is defined as f omega is equal to infinity power infinity f of t e power minus omega t into dt. Here, f of t is the time domain signal and f of omega t represents its frequency components. The f of omega is equal to integral minus infinity to infinity f of t into e power j omega t dt. The Fourier transform changes time domain to frequency domain and back again. Now, let us see the properties of Fourier transform. The Fourier transform has several key properties, including linearity, time shifting, and frequency shifting. It also exhibits properties like convolution and Pascal's theorem, which relate time and frequency domains. Understanding these properties is essential for applying Fourier techniques effectively. The properties are given as scalar multiplication, that is, k into x of t in time domain, k into x of omega in frequency domain. Addition x1 of t plus x2 of t is equal to x1 of omega plus x2 of omega. Conjugation x conjugate of t is equal to x conjugate of minus omega. Duality x of t equal to 2 pi x of minus omega. Scaling x of a t equal to 1 by magnitude of a x of omega by a. Time shifting x of t minus t naught is equal to x of omega into e power minus j omega t naught. Frequency shifting, time convolution x1 of t convolute with x2 of t is x1 of omega into x2 of omega. In time convolution, the convolution changes into multiplication in frequency domain. Next, frequency convolution. x1 of t into x2 of t is 1 by 2 pi x1 of omega convolution with x2 of omega. These are the properties of the Fourier transform. Inverse Fourier transform. Inverse Fourier transform is nothing but it is the reverse operation of the Fourier transform. That is, it converts frequency domain into time domain. So the inverse Fourier transform allows us to convert frequency domain data back to the time domain. It is given by f of t equal to 1 by 2 pi integral of infinity to integral of minus infinity to plus infinity f of omega e power minus I omega t into dt. This process is vital for reconstructing signals after manipulation in the frequency domain. Cosine wave into single frequency, sync wave into uniform band of frequency, Gaussian into Gaussian, double exponential into Laplace. Likewise, the inverse Fourier transform is used for manipulation in frequency domain. Image processing applications. In image processing, the Fourier transform is used for image filtering and enhancement. It helps in transforming images to the frequency domain where noise can be more effectively removed. Techniques like frequency domain compression utilize Fourier transform principles for efficient storage and transmission. Communication systems. Fourier transform plays a critical role in modulation and demodulation processes in communication systems. It helps analyze signal bandwidth and interference effects in transmission channels. Techniques such as orthogonal frequency division multiplexing, that is OFDM, rely on Fourier principles for efficient data transmission. The Fourier transform plays the major role in the biomedical applications. The Fourier transform is crucial in medical imaging techniques like MRI and CT scans. It allows for the reconstruction of images from raw data collected during scans. Additionally, it is used in analyzing physiological signals such as ECG and EEG, that is electrocardiography, and that is used for heart. Signal filtering. Signal filtering is a common application of the Fourier transform in removing unwanted frequencies. High pass and low pass filters are designed in the frequency domain to enhance desired signal components. This technique is vital in applications ranging from telecommunications to audio engineering. There are some limitations for Fourier transform. Despite its usefulness, the Fourier transform has limitations, especially in analyzing non-stationary signals. It assumes that signals are periodic and can lead to inaccuracies when this assumption does not hold. Alternative methods such as wavelet transforms are sometimes preferred for better time localization. How wavelet transform is used as an alternative Fourier transform. The wavelet transform provides a multi-resolution analysis of signals, addressing some Fourier transform limitations. It allows for better time frequency localization, which is beneficial for transient signals. Wavelet analysis is widely used in applications such as image compression and feature extraction. The software tools for Fourier analysis are: there are various software tools and programming languages that facilitate Fourier analysis, such as MATLAB, Python, and R. Libraries like NumPy and SciPy in Python provide efficient implementations of FFT and other Fourier methods. These tools enable researchers and engineers to apply Fourier techniques easily in their projects. Real world case studies. Case studies illustrate the practical applications of Fourier transform in real world scenarios. Examples include its use in audio restoration and telecommunications for signal clarity. These case studies demonstrate how Fourier techniques can solve complex problems effectively. Future directions. The future of Fourier transform applications may involve integration with machine learning techniques. Advances in computational power will enable more complex signal analysis and processing. Research continues to explore optimized algorithms and new applications in emerging technologies. Conclusion. The Fourier transform is a fundamental tool in signal processing. Its ability to analyze and manipulate signals in the frequency domain is invaluable. Understanding and applying Fourier principles is essential for advancement in technology and science. These are the references to know more about the Fourier transforms and its analysis. Thank you everyone. Please like, share and subscribe my video.